Welcome to the preview video for the 7th class in Math S-322. Two topics for today, power series and uniform convergence. Power series are very important because Taylor series are among the most significant applications of elementary calculus. Uniform convergence is another of these topics you may well never have heard of before, but we're going to have to face up to it in order to address the issue of when a function defined by a power series is continuous. The key theorem here is in fact difficult enough that I'm not going to hold you responsible for it, but I will do my best to prove it in class. So let's get going. A power series is an infinite sequence, an infinite series where the general term is some constant a sub n times x to the nth. So a sub n is a sequence of real numbers, and that we can use to define a function of x. If there's some set of real numbers for which this is a convergent series, then the power series defines a function of x, and the values of x for which that happen depends on the coefficients. It turns out there are only three possibilities. You can't get an arbitrary set. The most standard one is that this is a convergent series for x in some interval between minus r and r, where the quantity r is called the radius of convergence. So the convergence is on an interval that's centered at 0. It could be an open interval, it could be a closed interval, or it could be a mixture of open and closed, like the interval that is open at minus r and closed at plus r. Here's an example with which you may be familiar. The natural logarithm function of 1 plus x has the power series expansion x minus x squared over 2 plus x squared over 3, and so on. If you plug x equals plus 1 into this, you get 1 minus a half plus a third minus a fourth, and so on. That converges to the natural logarithm 2, albeit only conditionally. If, on the other hand, you plug in minus 1, you get minus 1 minus a half minus a third minus a fourth. That's the harmonic series with minus signs thrown on. It's a divergent series. So in this case, the power series converges at plus 1, doesn't converge at minus 1, and here is the full interval of convergence. Teachers of calculus like these for exam problems because you could force the students to use something like the ratio test or root test to find the radius of convergence, and then apply more subtle tests like the alternating series test and the integral test at the endpoints. Second possibility. This series converges for all real values of x. That will frequently be the case if there's a factorial in the denominator of the coefficient. And this case, which looks at first outlandish, is actually very common. In particular, the power series for the exponential function, the sine function, and the cosine function all have an infinite radius of convergence. The third possibility is that this power series only converges when x equals 0. It converges when x equals 0, of course, because all the terms are 0. In that case, we say the radius of convergence of the series is 0, and such series are quite useless, even though it's possible to write them down. How do you find the interval of convergence? Well, Ross has a set of rules for doing this, but I have a simpler way, which I'm going to encourage you to use. Just apply the root test or the ratio test to the power series. What you will find is that the test works on some interval between minus r and plus r, and it fails because the root or the ratio is 1 at the endpoints. In that case, you have to apply a more subtle convergence test. We got lots of practice with this in class. Now, what about the continuity of a function that's defined by a power series? Clearly, this power series, wherever it converges, defines a function of f. Furthermore, each of these functions is clearly a continuous function. The sum of two continuous functions is continuous, and by induction, the sum of n continuous functions is continuous. So as long as we stick with the partial sum, the resulting f sub n of x has to be a continuous function. What happens, though, if we take the limit as n approaches infinity? What's true for finite n is not necessarily true in the limit as n approaches infinity. And in order to show that this f of x defined by an infinite series is continuous, we need to introduce a new idea. We have to show that f sub n of x converges uniformly to f of x. And this is tricky. At least you've seen uniform continuity already. And uniform continuity, you'll recall, means we agree on epsilon first and hold off on choosing the point at which we're going to try to show that the function is continuous. Uniform convergence is a similar use of the adjective uniform. We're going to choose the epsilon first and hold off on choosing a point x in the domain until last. So let's consider a sequence of functions defined on some subset of the real numbers. It might, for example, be the function where f1 is f of x equals x, f2 is f of x equals x squared, and so on. All these functions are defined, well, they're defined for all the real numbers, but in particular, they're defined on the subset from 0 to 1. If for any x in the set S, the limit of the function values f sub n of x is f of x, then we say that this sequence converges to f of x, but we say it converges only pointwise. And the problem here is that in order to show this convergence, we may need a different rule for selecting the capital N depending on the point x. We say that the convergence is uniform, and you're not going to get this on the first try, but I'll present the definition, and then we'll work on it in class. The condition for uniform convergence is first we agree on a positive epsilon. That's the challenge, and you have to respond to the challenge with a one-size-fits-all capital N. Your capital N has to have the property that if we pick any little n greater than that capital N, the difference between fn of x and f of x is less than absolute value than epsilon, and that works for all x. So that's why we're using the term uniform. First we choose the epsilon, and then the very last choice is x. This has to work for all values of x. Another way of stating this, if little n is greater than capital N and x is some value in the domain, f sub n of x lies in the interval between f of x minus f of epsilon and f of x plus epsilon. So we need to find this one-size-fits-all n. Here's another equivalent statement of the definition that you might prefer. You've got a sequence of functions defined on a subset of the real numbers, and we say it converges uniformly to a limit function f if and only if the largest difference between f of x and f sub n of x as n approaches infinity is 0. Let me now try to convince you that it's possible to have pointwise convergence without uniform convergence. And I think the simplest example is one I've already mentioned. F sub n of x is the nth power function, and the set we will choose, capital S, is the closed interval from 0 to 1. Okay, suppose that x is less than 1. Any number less than 1 raised to the nth power gives a number less than 1. And furthermore, as the power gets larger and larger, the value gets smaller and smaller. So if you take a value less than 1, like 0.7, and raise it to a very high power, you get something very close to 0. That means as long as x is less than 1, the limit of f sub n is 0. But suppose x is equal to 1. 1 raised to any power is 1, so as n approaches infinity in that case, the limit of the function is 1. In other words, pointwise, this sequence converges to a function f sub x, which equals 0 when x is less than 1, but which equals 1 when x equals 1. It's a discontinuous function. This is a little bit alarming. We have a sequence of continuous functions converging to a discontinuous function. What's gone wrong? The sequence isn't uniformly convergent. And how do we show that? Well, in this case, it's fairly easy. Suppose we pick epsilon equals a half. Sounds like an easy challenge to meet, but in fact, in this case, it's impossible to meet. For any little n, I can find a value very, very close to 1 where the nth power of that x is equal to 1/2. So there's no one-size-fits-all value of capital N, and the convergence is not uniform. Fortunately, there are circumstances under which we can prove that the limit of a sequence of continuous functions is continuous. If that sequence of functions converges uniformly to a limit function f, then the limit function is continuous. How does this relate to the example I just showed you? In the example I just showed you, a sequence of continuous functions converged to a discontinuous function, but the convergence wasn't uniform. This is actually not hard to prove. We'll do it in class. If each individual function in the sequence is continuous on x, then so is the limit function. You're thoroughly familiar now with the epsilon over 2 trick. You've been using it since the second day of class. This proof uses an epsilon over 3 trick, which is almost as generalizable as the epsilon over 2 trick, though we won't see that many more examples of it in this course. Now here's the key result. It's hard to state and even more difficult to prove. I'll denote by capital R the radius of convergence of a power series, and I'll choose some value R1 that's positive but less than R. In that case, I can prove that on the closed subinterval from minus R1 to R1, the power series not only converges, it converges uniformly, and by the result I just stated, the power series therefore converges to a continuous function. So you've got this interval going from minus R to R. If you take a subinterval that goes only from minus R1 to R1, the power series converges to a continuous function on that subinterval. What about the full interval from minus R to R? Well, you already know that the power series may fail to converge at one or both of the endpoints, so we'll only look at the open interval. In this case, we can prove that it converges to a continuous function, but the convergence is not necessarily uniform. Suppose the series converges at an endpoint. To show this, we generally require an extra convergence test, and it turns out that if the series converges at an endpoint, the function is continuous there. This theorem is attributed to the great Norwegian mathematician Niels Abel. it is a very challenging theorem to prove. The proof is done in Ross. We'll look at one example in class, but we will stay away from the proof itself. The result, however, is well worth knowing because, in fact, it gets used in conjunction with functions like the arctangent function. Students love to integrate and differentiate power series term by term. It's kind of fun to differentiate the Taylor series for the sine function to get the Taylor series for the cosine function, and so on. And it turns out there are some results about integrating and differentiating series that are not hard to prove at all. Namely, that both the function that we get by differentiating the power series term by term, you'll recognize a sub n, x to the n gets differentiated to get n times a to the n times x to the minus 1. We can also integrate the series term by term, raise the exponent by 1, divide by n plus 1, and both these series have the same radius of convergence. The interval of convergence is not necessarily the same. Generally, the integrated series is better behaved at the endpoints. The differentiated series is worse behaved at the endpoints. But the radius of convergence is the same. Finally, one last result. This involves integral calculus, but you all know calculus. You're learning real analysis. So let's suppose we have a sequence of continuous functions defined on some closed interval, and suppose further that the sequence converges uniformly to a limit function, which is also defined on that interval. Then, and it's not too difficult to prove, the limit of the integral is equal to the integral of the limits. That's obvious, you think. How could it be otherwise? Well, it's not true in general, and the simplest example is this. For f sub n, let's consider a function that has the value 1 only between n and n plus 1. So, for example, f6 would equal 0 everywhere except that it's 1 when x is between 6 and 7. Clearly, the integral of any such function is going to be 1 because the area under the graph is 1. On the other hand, the pointwise limit of that sequence of functions is the 0 function. What's the value of the limit at x equals 1,000? Well, sooner or later, x is going to be bigger than 1,001, and the value will be 0. So the integral of the limit is 0. The limit of the integral is 1. Why can they disagree? We don't have uniform convergence. And I'm off to get a drink of water, and I am done.